So I can start. So what happened? We have 1, 2, 2, 2, 2, 3. So now we just observe that even equivalence of 3 to 4. What am I saying? So since okay, exactly, ACF0 is complete, and C is a model of ACF0, then this equivalent is exactly the other part of problem we used before. So this equivalence given by problem 12.1. Yes, it was saying exactly this. If we have a complete theory and its model, then statement, sentence is true in this model if and only if it's a logical implication of the theory. Okay. So this is exactly application of this situation to ACF0 and C. So we have now 1 implies 2 implies 3. 3 is equivalent to 4. So to finish, so what's the picture? 1, 2, 3, 4. So to finish, we need implication from 3 to 1, for example. And this is what we will show. So 3 to 1, okay, as we discussed in problem session, this will not be a proof of contradiction here by contradiction, but by contrapositive. So we will show, but a bit funny, because it will use one of the previously shown implications, that not 1 implies not 3. Okay, now I really need to remember what were these problems.
We need to show for each model of ACF0, phi is satisfied. Since it's complete.
No, not for all. Problem 12 was saying that if we have such a situation, that there is complete theory, a sentence, and its model, then exactly this happens. The formula is logical consequence of theory, if and only if it is true in this model. Since it's complete, it is also true in all the models, it's equivalent, but we can focus on one. Okay. Okay, so assume not 1. Okay, so we have the sentence phi all the time. Assume not 1. So it's not true that for almost all primes something happens. So its negation is that there are infinitely many primes that the opposite happens. Okay. Such that it is not true that it is that this phi is true in FP arch, that means that negation is true. Yes, in a model, either something is true or its negation is true. No other option. So such that FP-arch, in FP-arch, not phi is true. No. Okay, shall I? Yes, the statement was, okay, I can write it, so in 1. Okay, so let P be the set of all primes. So 1 really says there is X in P finite such that for all P here FP-arch C. So negating is okay, negating. For all, okay, maybe that's maybe it's not the easiest way to negate. There is, should have probably written it somehow differently.
There is some prime bigger than this, all of that.
There is P. Yes, but I'm making it too complicated. So this should be the same, that there is infinite subset of primes such that this negation of phi happens for this FP-arch. Okay, if there was a okay, so I should continue this. So then, if I take, okay, okay, so let y, so now I am showing that this is really the negation of 1, which takes a bit longer than I expected. So let y be the set of all primes such that so I'm saying this set cannot be finite, because then I can take it as an X there and find something more. Finite, then by above there is P contradicting definition of Y, because Y consisted of all of this P such that
Shouldn't we write for all x infinity P?
no. Negation. Now it should be this. So how do we? So let me finish this contradicting. So
Can I-
yes.
So we already proved that, or said that Gödel's completeness theorem, this implication models is equivalent to proofs.
Yes.
If ACF0 models phi, then this means that if and only it proves phi, right?
Yes.
So this means that there's a proof of phi from ACF0 which uses, a proof is finite, so it uses finitely many things,
Yes.
which proves it. So it means that there's a finite subset such that which
Basically,
models
yes.
phi.
Uh-huh.
So this means, this finite set can only contain finite many of these phi-n's, right? Among the axioms, which is saying that the characteristic is not P1, not P2, not P3. So
That would be another.
anything bigger than that characteristic, for every, this means that this finite sentence is satisfied in, finite set of sentences are satisfied in any FPI which is of characteristic bigger than.
Yes, that would be another proof without negation, but I guess still we have to fight with negating almost all.
Okay, I'm wrong, I understand.
Okay. So I could also get to this, but I guess this is how to negate for all. Okay, anyway, so we are here. Yes, what Özlem said was okay. I hope now that also that negation is okay. Yes, so negating almost. So negating for almost all is there is infinitely many, such that the negation of the other thing happens. And yes, okay, this was okay what you said, but here is this funny thing that we can use here. We can use the implication which was already proven from 2 to 3. But for the negation. And by this we get that ACF0 plus logical consequence is negation of phi. Yes, because for infinite many primes p it was true. This, so we use this implication just with another sentence here. So a bit funny thing that one implication is used in the proof of another implication, but the implication which was already shown. So now, since this is true and ACF0 is consistent, it is not true that ACF0 implies phi. Which is the negation of 3 as we wanted. But yes, okay, we could at this moment use Gödel as well. Yes. Okay, which we didn't prove, so okay. So this has the advantage that here we proved everything. Okay, but this would be kind of faster. Okay. So that finishes this whole Lefschetz property. Okay. This is also in algebraic geometry, people like to say Lefschetz property, but then I think they mean that if some algebraic geometric property is true for complex numbers, then it's true for all algebraically closed field of characteristic 0. I think this is just geometric usage of the Lefschetz property. Yeah, and sometimes there are things for which Lefschetz property applies, this geometric one, which are not like sentences. So it's kind of
maybe not first order.
Maybe not first order, or we didn't understand yet how it is first order, but still this geometric Lefschetz property holds. Because maybe, okay, probably it's also a bit more.
Can you give an example, little example?
Okay, so let me think by erasing this part. I come up. Okay, so the best, I'm not sure now.
There were things about ramification and primes. Something true.
But usually it is that there is some geometric property which can be shown by analytic methods for C, and then they conclude it's also true for others. But now I cannot think about any such non-trivial property. Yeah, okay, I can find something later. Okay, but now I cannot come up with anything. Yeah, I will try to remember. Okay, so this finishes what I promised in the first lecture. So we gave these proofs. Okay, we finished proving the model theoretic theorems used to prove these things about fields. Now the last topic, okay, which actually will be another theorem about algebraically closed fields, which have a model theoretic proof, Chevalley theorem. But the related model theoretic concept is called quantifier elimination. Okay, so as we see this property here, so maybe first definition, a theory T is model complete if any extension of models is elementary. That means if a model has a substructure which is also a model, its elementary substructure. But this may be faster. Extension. So in this terminology, MT2 says, huh? Okay, so I'm saying that is if M is model of T, N is model of T, M N is also a substructure, then it's always elementary. Okay, this is the property. But as I was talking about extensions of fields, so in this sense I'm talking about extension of models.
So CF0 and CFP is model complete?
Yes, ACF even.
ACF.
So MT2 says basically that ACF is model complete. But actually it satisfies something stronger. So our aim is that ACF has a stronger property, and this is called, which I will explain later, I guess on Saturday, quantifier elimination. Okay, stronger. So I will repeat myself a bit. So which implies, which in general implies model completeness. Okay, so I'm just saying this so you can kind of focus yourself that now we want to show that something even better is true about ACF, and this is better than this model completeness. Okay, but I'm not saying exactly what it is yet. Before that, I will talk about definable sets. So first, some general definition. So again, we have language, L structure, and fix some n tuple of variables. And now, to any formula with this tuple of free variables over M, we associate a definable set in the nth Cartesian power of M. So, for an LM formula, dx, so these are free variables, define, define the notion of definable set. So a bit definition of definable set. I will use such notation. It's like set of realizations in the structure of this formula. You may think it's like solution of some equation or systems of equations. Okay. Not perfect, but not a bad intuition here. So such tuples in M to the n, universe to power n, that this formula is true in M when we plug them here. So I don't know, here we have... For example, it's a definable, yes. Okay, I will give examples. Yes, yes, centralizer of a given element. It would be something like this. So just, okay, not very enlightening picture. We have this M to the n, and inside M. So now a subset X is called definable well, and now several adjectives. So in structure M over parameters M, we could restrict parameters, but now we don't care about it too much to smaller sets, if it is of such a form. Yes, so it's okay. Could be thought as some kind of geometry that on each power of M we have this collection of subsets which are definable. Like in topology, we have collection of subsets which are open or closed. Okay, in differential geometry, we have collection of smooth submanifolds, etc. Here we can think kind of geometrically. We are really interested. So that's really what kind of model theory does. We are not really interested in all subsets. We are interested in definable subsets, definable relations between them, and what we can express definably. Okay? And which will be important in this context. So similarly, as in 2, X is called quantifier-free definable. If X is of such a form where X has no quantifiers. Yes, formula which doesn't involve any quantifiers. Yes, of course, there are such formulas which do not involve any quantifiers. So somehow idea, no. So idea, those are simplest definable sets. Okay. If we know more about language, there may be even simpler ones, but in general, those are kind of the simplest. And if quantifiers appear, they become more and more complicated. So you can already guess what quantifier elimination will be. But I will say it, I think, next time. Okay. So still some obvious properties. And then some examples. So how the sets are obtained from formulas. So if we have conjunction, and we take realization, then, okay, what should it correspond to?
Phi x bar n intersection.
Yes. So it is obvious. Similarly here, if we have this junction alternative, then it is union.
This is quantifier elimination.
But still I haven't defined it, but okay. Negation, okay, we assume we have fixed this n. Negation is the complement or complement. Which one is which one? Complement. And complement is to say something nice, yes. Have a tendency to confuse the two.
Yeah, both pronouncing it wrong, so.
But one is E, one is E, kind of. Okay, so those are obvious, but now what happens with quantifiers? So I said it quite precisely. Let me put, so existential quantifier is enough to understand everything, because other comes by Morgan law and negation. So if I quantify, let me say the last n minus k something variables, and then I take definable set corresponding to it, then this is projection, image by the projection map. So where this is projection on the first k coordinates. Okay, so. Okay, this is also kind of obvious, but maybe one has to think slightly more what happens if you put existential quantifier. But now you can see what's happening. Okay, so those, okay, again, we have this correspondence. Further order. This complement. These are so-called Boolean operations. So actually this is not only any arbitrary collection of sets, these definable sets, but this is Boolean algebra or Boolean subalgebra of the algebra of all sets. So some kind of algebraic structure on it, not extremely interesting. And this is projection. Okay, so you can think first On each powers, you have this quantifier free ones, which are closed under Boolean operations. So if you want, you start from basic formulas and sentences in the language, so relations and sentences. And from this, Boolean operations, you create all quantifier free ones. But then you keep projecting, applying again Boolean operations, again projecting, and that's how it gets more and more complicated. Okay, and it can be pretty complicated, as we've seen examples.
Yes. So for a prime polynomial, the zeros of this polynomial is kind of simple.
Yes, even simpler. So I will talk about it, because it's kind of closed. There is this notion of Zariski closed, but only specific for fields and rings. So even better than quantifier free, it's even kind of closed. Then from this all quantifier free, I will tell is kind of called constructible, but then you keep projecting, and actually in algebraic closed fields, you don't get anything new. That will be Chevalier theorem. That projection of this constructible is again constructible, but this will be next time. Okay. So this is this complication at some point stops.
Is it same as Chevalier theorem?
Yes. So Chevalier, okay. Maybe I will check history next time. Yes, Chevalier theorem is basically quantifier elimination for ACF.
I don't really understand that there is means projection, but maybe I should think more.
Okay, let me, okay, actually there were no problems yet. So let me make it a problem. Because yeah, this is something that one really should think. Did I skip? No, okay. So let this be problem 15. Okay, enough for n equal 2, k equal 1, not to get to. Yes, it's good to think about it, that you see how it. Okay, so examples. So at least about fields. So first, K is any field so far. L is the language of rings. So any set of solutions of a system of polynomial equations over K in n variables, which I'm not writing, is a definable subset So obvious examples. Where it will be just one equation for simplicity. So fees. Oh, hyperbola. So such sets are called, as I said, Zariski closed. I should say is actually also quantifier free definable. But they are clearly the even simpler than simplest, because we really take equations only. We can also negate equations and then get something more. So their Boolean combinations.
Can you write alpha in K, alpha Y is equal to X to the 2?
Co sorry?
Sorry, I'm confused. Quantifier and parameters.
Okay. Parameters. Yeah, so there are also no parameters here, but I could write some parameters, of course. Are classically called constructible sets. So, of course, for example, a point is Zariski closed, x equals 0. So like this one. So phi is here, let's say negation that x equals 0. Okay, so this point symbolizes that it's not here, but it's also 0. So in this case, quantifier free definable sets are exactly constructible sets. Quantifier free definable. This is just giving different names to the same thing. So we start from these solutions of equations, and then we apply all these Boolean operations. Okay, so if we, actually it's topology, which can be shown. So did you have algebraic curves yet, or not? Okay, it will come there. I will take it, yes, so it comes there. So intersection of two, which is quite clear, yes, if you take equation and add more equations, it's still equations. So it's closed under intersections. So they are really closed set of some topology. But then open sets correspond to taking these complements, like Boolean operation, but it's more. You can intersect open and closed, take a union, and this you get all constructible sets. So you can do it in any topology, yes, like this. So in this case, these are exactly constructible sets. If this Zariski topology are exactly quantifier free definable sets for fields. And okay, I guess I will just say a bit more, but to give next examples on Saturday. So the point is that actually we will show one direction, but it's even true that field is algebraically closed if and only if they are all definable sets. So even two directions. Okay, so algebraically closed fields have quantifier elimination, which means for algebraically closed fields there are no more definable sets than quantifier free definable, which are the same as constructible, and which I will not discuss. It's also true the other way. If such field has such a property, it must be algebraically closed.
All definable sets are constructible?
Yes, in algebraic closed fields. And if field has such a property, then it must be, which I will not. Huh?
Is it about Hilversum's-Schellensatz?
No, it's about Chevalier theorem. It's about quantifier. It's about quantifier elimination. Okay. So actually, it will be about. I will show at this idea of the proof. This will really correspond to the fact that if you have algebraic closed field and isomorphism between subfields, it extends to automorphism. This will be the property responsible for that. Okay. So this will be on Saturday, so thanks.